It's not, it's only because this sort of light messes with my camera. I'm not a vampire or anything. All right, so welcome to Calculus 2. Everyone's in the right place? Okay, what I thought I'd start out with is I want to talk a little bit just about calculus before we start getting into all the administrative stuff. Let's see. I only have one student here. Did I have Cal 1? Oh, there, 2. Yeah. Where'd you come from? And then you did Cal. Yeah, that's right. Okay, that's right. So otherwise, I'm not quite sure what your Calculus 1 background is, like where you came from, who you took. So we'll see. All right, we'll see where you are calculus-wise here coming in. But let's just talk about calculus itself. You know, calculus, what we're doing here, I like to look at this class as, I know it's like you need it for your major, right? Electrical engineering, computer science, whatever it is. But, you know, when we're studying calculus, you have to always keep in mind that we're looking at, you know, hundreds of years of human thought that we're trying to compress down into 3 semesters, right? I mean, it's Cal 1, 2, if you're going to take Cal 3. How many of you need Cal 3? Okay, so not quite half of you. All right. So, you know, when we think of it that way, I like to look at this as being almost like a history class. It's just there's a lot of mathematics involved in it. We are in no way discovering anything new, right? But we want to look at the progress of human thought. So these major advances in mathematics that happened over the last few hundred years, 1,000 years, you know, we are going to try and absorb that in a very short period of time. So these thoughts, these theorems and stuff are profound, and we're just going to be like, oh, okay, and we just use them, right? So I just want us to keep in mind the whole time here that this is really like a history class, a short little glimpse into the history of math. So let's talk about Cal 1 first. All right, that was 2413. Cal 1. Let me see if you can help me summarize what Cal 1 was all about. Any thoughts? Derivatives, okay. Okay, so let me do that. Limits came first, so I'll say limits. And then derivatives. So if you were trying to explain Cal 1 to somebody and you had to sum it up in one word, I think derivatives would probably be the word. In fact, most of the time we call calculus 1 differential calculus. Differential meaning the derivative, right? So it's all about the derivative. We find slopes of tangent lines, right? So geometrically, what we did in Cal 1 was we took a curve, picked some arbitrary point, went to that point, and we could find the slope of that line using the derivative, right? What else did we do in Cal 1? What's some of the stuff that was challenging that you didn't enjoy? Optimization, okay, like graphing using calculus, so optimization. Okay, optimization is like, you know, a farmer wants to build a pen, he's got, you know, 300 feet of fence, blah, blah, blah. Okay, so those are usually challenging because they're word problems, right? Okay. What else did you say? Optimization? Oh, graphing, right? Yeah. So I'm going to call that curve sketching. Now, curve sketching, that section is very involved because, you know, you're going to wind up taking first and second derivatives, then doing all these different tests and solving equations and testing points. And I mean, there's just a lot involved. And so curve sketching is actually a very nice topic in terms of kind of like getting an overall view of what the student can do. If they can do a complicated graph by hand, then it shows that they understand. But in reality, like, we just have computers to sketch curves, right? So, all right. Anything else? Y'all are leaving out something. Antiderivatives at the end, right? You started to get into that. See, you've already erased it from your memory because you probably didn't enjoy it that much.
There was one where it was like you had to find it to the 5th decimal point. I forgot what it was called though. It was towards the end.
Like Newton's method
yeah.
thing? Newton's method, yes. Some instructors don't cover Newton's method, so that's kind of an optional topic. You know what I'm talking about? Okay, how about I give you something as a hint? A spherical balloon is inflated, okay, related rates, right? Have you already erased that from your memory? Okay, related rates. So related rates, what I've always found fascinating about related rates is that the main idea behind this is that if somebody gives you any equation, even if it's a well-known one, like the one I like to use in my class is this one. I think this is like the ideal gas law or something like that. I'm not a chemist, but it doesn't matter. Go grab me any equation from any field. Doesn't matter what field it's from. And if you want to know the rate at which any of these variables is changing with respect to the others, all you have to do is use implicit differentiation. And so you could differentiate this with respect to P, which is pressure. You could differentiate this with respect to volume. You could differentiate it with respect to temperature. You could differentiate it with respect to time. It does not matter. Okay, and so this is a really, really important topic, but it involves word problems. So again, along with the optimization, these are usually the two most challenging sections because coming up with the math behind them requires translating the word problem, right? Okay. All right, I think that's pretty much it. For those of you who came in, Cal 2, you're in the right place? Okay. All we're doing is we're talking a little bit about what Cal 1 was, and now we're going to talk a little bit about Cal 2. So with Cal 1, I would say, of course, the limit for sure is important, but the main takeaway, derivatives and slopes of tangent lines, right? Everything else is kind of like a result of that stuff. All right, now what is Cal 2 going to be about? Well, you might be repeating the course, so you might already know this, but Cal 2, what we really focus on are what are called antiderivatives. All right, so all we're going to be doing towards the beginning of the class is we're going to be taking a function and we're going to be like, hey, that function is the derivative of something. And so you have to go backwards and figure out what it was the derivative of. So I'll give you a quick example. If I tell you that I have a function f of x equals 2x, then that's the derivative of something. What is that the derivative of? So I'm going to call it capital F. What?
2x squared? Or no,
Just x squared, right? X squared? Because if you take the derivative of this, you get this, right?
Yeah.
And then we'll find out later that you can actually add any number to that, and it would still work, right? Because the derivative of a constant is 0. So what we're going to be doing is the reverse process. We're going to be going backwards. And that is inherently difficult to do, all right? And that's why you have to be really good at going forward, derivatives, in order to go backwards, because you have to see these things kind of before you even, you have to think through, oh, I recognize that. Oh, I see that that was a product rule there. I see a chain rule in that. But if you struggled with product rule, chain rule, quotient rule here, then it's going to be exceptionally difficult here. Also, when it comes to derivatives, I just gave you the rules. There's the power rule. That's how we go from here to here, right? With the power, we have the power rule, we have the product rule, we have the quotient rule, we have the chain rule, right? Otherwise, it's something like if I ask you a derivative of sine of x, you just have it memorized, right? So in Cal 1, we have like formulas. And students usually do really good with like, show me a formula, I'm a robot, I can do the formula, and eventually get good at it, right? But in Cal 2, there's no formulas. There's procedures that we attempt, and they don't always work. And so things become more and more complicated. So it's very difficult on my end as a teacher to teach instinct. It's hard to teach instinct in Cal 2, and that's what you need is instinct. But that instinct comes from your comfort level with Cal 1. So if you limped through Cal 1, I'm just telling you it's going to be a challenge. It's not that you can't do this, but just be ready to go get really, you're going to have to go back and review and get really comfortable with the derivatives, or else you're going to retake this class 3 times potentially. So I just want you to know that, all right? And I should also point out that it is okay to have to repeat this course, okay? I mean, like if you get, if you take this class and you're challenged by it and you don't pass it and you have to retake it, it's not the end of the world. That happens for a lot of students, all right? This is kind of like This is in the calculus sequence, this cal 2 is the 1. Don't let anyone else tell you, okay, that this is easier than cal 1 or something. Don't believe any of that. That's all hype, all right? This is the hardest calculus. Cal 3 is usually easier than this one, all right? All right, so antiderivatives. Now, geometrically, the derivative gave us the slope of the tangent line here, right? So geometrically, we're going to actually have something from this also. What we're going to find out later is that the antiderivative allows us to look at a curve and then take like 2 endpoints of that curve, drop these lines down, and the antiderivative will somehow be able to give us the area under that curve. It's some magical formula that we're going to have. It's actually related to what's called the fundamental theorem of calculus, but that area can be found under any curve by simply finding the antiderivative of the function. So no more slopes of tangent lines, instead we have areas. So we are going to spend the first third of the course just practicing how to find antiderivatives. And then we're going to start talking about areas. And then after we do areas, what we're going to do is, I don't know if you can visualize this, but can you kind of see what would happen if I took this graph, took the whole graph off the sheet of paper, and then just swung this entire graph around the x-axis? Do you see what I would get? It would be kind of like three-dimensional. I would get almost like this weird, it would be like a solid. It almost look like a bell that's like sideways. Do y'all see that solid? Okay, so what we'll be able to do here is we'll actually be able to find the volume of this. Okay, so how much space it takes up. And then we'll do some other things where we'll actually take this curve. And it turns out that finding the area and the volume, the formulas are not that bad. What gets difficult is when we move this graph up and revolve it around a different axis or something, then the formulas start getting a little weird. But the mechanics of it, if you can do this part of the class, this part's going to be pretty easy. All right. Then what we do is we'll take that curve again, all right, and then imagine just taking it off the piece of paper, all right, just the curve, just pull it off, and imagine it's just like a string. And then just straighten it out, okay, and tell me how long it is. Okay, so that's called the arc length. So we're actually going to find the length of this curve. All right, does that make sense? And then we'll go back and we'll look at this again, and we'll say instead of talking about the volume of it, let's talk about the surface area. So like if you had to paint the outside of that bell, how much surface is there? So we'll do areas, we'll do volumes, we'll do arc lengths, and we'll do surface areas. Understand? And that will be our applications. We'll try and get some physics applications in there. We might do, most of the time I do work. If you've taken physics, you know what work is. Do work, or maybe we'll do like hydrostatic pressure. I'm not sure. But there's a whole section on applications, and I get to like pick which one we cover. And that's it. Okay, so that's the second third of the class. This is, by far, this is difficult. This is mildly difficult, all right? And then we get to the last third of the course. And this last part is called series. And that is the hardest part of the class. And this is, let me tell you why. Number one, a lot of students, maybe in your high school or somewhere in your background, have done derivatives and some antiderivatives, and maybe you've seen some of this in high school. A lot of times, students have never seen series. And so it's brand new. It's at the end of the course, so you're already kind of exhausted. And it is a lot of material to cram into. We started on Halloween. October 31st is Halloween, right? That's when we start series. And we spend all of November on it and a few days in December. So we're talking, at least 3 or 4 weeks on that topic, all right? So I've given you some idea of what these are, but how we'd use antiderivatives, but what are series, right? Like what is a series? And let's not get too much into it, all right, because we will spend time on it. But just to give you an idea, like what would happen if I took like 1 plus a half plus a third plus a fourth and I kept doing that forever. Like, would that add up to be a number, or would that just become infinitely large? What do you think? What's your gut tell you here? So you take one. So imagine like you have a big old tank, all right, and you pour 1 gallon into it, and then you pour half a gallon into it, and then you pour a third of a gallon into it. Is it going to overfill that tank at some point?
Eventually, it'll take a long time.
It might take a long time, but it will. So do you understand what the question is? It's either going to overfill that tank or it's not. Could it possibly not? Well, this one, it does turn out that this does become infinite. It does overfill the tank. All right? It does. But if I take something like this and I change what I'm adding up, okay, so that's a different sum. Okay, it's 1, it's 1/2, but then it's 1/4, 1/16, 1/32. These are smaller bits, aren't they? This one, it turns out, does not overfill the tank. All right? So what we have to do is we have to look at these series. We call these series. We look at these series and we try and figure out whether or not they converge, which would be they add up to be a number, or they diverge, which means that they become infinite or they don't do anything. Like here's an example of one that it's hard to understand what's happening with this. 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. What does that add up to be?
Or isn't it 1/2?
Well, yeah, I mean, is it? Yeah, I mean, right? What is it? I mean, you could argue that it's 0, right?
There's 3 answers.
Yeah, it could be maybe be 0. You could. How would you argue that it's 0? Those are 0. Those are 0. Those are 0, right? And you could argue that that would be 0, but then you could argue the same thing for 1. Because if you just cover up this 1, then that's 0, that's 0. You see what I'm saying? Like these 2 are 0, those. See what I'm saying? So you could argue for 1 just as well. So it gets weird, all right? This series, we will say it diverges, which means that it doesn't go to infinity, but it doesn't go to a number either. And then the big result of this section, we'll have to spend a bunch of time talking about this, but the big result of this is to learn that every function that you've studied in your life that is well-behaved, sine, logarithms, exponential, all your polynomial functions, quadratics, everything that you've studied can be written, well, it can be written as some sort of series of power functions. I'll give you an example. And if this seems like, well, I don't know what he's talking about, don't worry about it, all right? Everyone here is familiar with the function e to the x, right? It's the exponential function. We know that e is about 2.718, blah, 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 right? And if we plugged in, e squared on our calculator, we would get a decimal, wouldn't we? Well, what we'll learn is that this right here is actually the same as 1 plus x plus 1/2 x squared plus 1/6 x cubed plus, and this actually goes forever, right? It's an infinite series of power functions. See how each of these is a power function? Every function can be written as an infinite series of power functions. And these are what we call Taylor or Maclaurin series. And this is the way a computer calculates e. So when you go to your calculator and you type in like e squared, it's actually not doing anything with e. It's actually putting a 2 here, a 2 here, a 2 here, and it goes out maybe 100 of these things and then stops calculating and then gives you the answer. So that's the way computers are operating. They're using series as opposed to, this. Like your calculator doesn't really understand what this is. Does that make sense? All right, so we will get into that. That's a long ways out. But that's kind of a Cal 2 in a brief summary. Yes?
So in that like 3 second of time, they do that like a bunch of those to figure out the series?
What now?
You're saying a computer that they do the...
The computer will not figure this out. The computer has this preset in the memory.
Oh, okay.
Okay, so this has already been established. So when you type in, e squared, it calls up this function and just plugs in, because your calculator can do arithmetic very fast, right? It can do these squareds, and that's multiplication, right? So it can do multiplication and addition quickly. So it just does that. Does that make sense?
So it does all that just
when you hit enter. Yeah, plugging it. Well, I mean, yeah, think about how fast computers are. I mean, you can do a lot of, a computer can do a lot of operations in, right?
Yeah.
So it might be doing 1,000 computations there and giving you the result before you can even blink your eyes. Yeah. All right, so that's Cal 1 and Cal 2. Let's not talk about Cal 3 because there's not a lot of you going to Cal 3 and I've already eaten up 20 minutes of class. All right, all right, let's talk a little bit about safety. So we have 2018, it's a crazy world we live in, right? So this door, it's unlocked. Do we want to keep it unlocked? You want to keep it unlocked from the outside? Y'all don't care? All right, so we'll just see. I guess we'll leave it unlocked. So if there's an active shooter, right, our options are to go out that way, to stay here, or to exit that window. So now this is good to know, right? Because this window actually, believe it or not, there's an awning right here. Even though we're on the 3rd floor, it's 3 feet down right here. So you can jump on that awning, you can go down, you probably have to jump off, and that would be 1 story. You'd survive that fall, okay? So I think we have enough people in here to breach this window. Okay, so I've actually been, every semester I try and talk about exit plan, right? I've been doing that for like probably my entire career. And when I used to do it, people were like, this guy's crazy. He's paranoid. And now it's like, yeah, we should probably think about what's happening if there's someone shooting up the school, right? It's pretty sad. But that's our plan, right? And this is also a legislature passed a law a couple of years ago. This is a concealed carry campus. So there may be people here who are concealing. So we have that also, so, all right. Should we talk anything else about that? Safety or anything? Any ex-military in here that wants to say they're ex-military? No? Okay, usually my ex-military guys are like, I got the door, man. I got the door, Yeah, I had a guy a couple of semesters ago, he was a riot. And he was like, oh, I'm carrying, man. He's told everyone, I'm carrying, man. I protect everyone here. It's like, okay. All right, do we want to look at the syllabus? Does everybody know how to get into Canvas? Anybody have no idea what Canvas is? Like, now's your time. All right, you have a quiz, an online quiz due in 2 days, yeah. Now, I don't normally give quizzes online. This is the only one all semester. So I'm getting into Canvas now. If you have no idea what I'm doing, then talk to me after class.
You teach Calculus 3?
I do teach Cal 3. Not this semester, but I am.
How many teachers here do that?
There's usually like 2 of us. Usually Roy does it, and there might be someone that does it at night. I'm not sure. Cal 3 is fun. Cal 3, I'll summarize Cal 3 in a few words. It's calculus in 3-dimensional space. So it's everything that you do in Cal 1 and 2, but in 3-dimensional space. So we're not adding in, it's still differentiation and integration, but it's now we take our functions into 3 space instead of on a flat sheet of paper. So it's fun, it's very visual, and I like it. Okay, so here is our course. I'll look at the student view so it kind of looks like what you'll see. So this is it, and right here with these red asterisks it says due next Wednesday, or this Wednesday, before class. So you just click on that, and all that says is you've read the syllabus and you understand the requirements of the course. All right? That's my way of getting a signature. That way, if you're like, hey, I didn't know, I'll just go back and be like, yes, you said you did. So I'm asking you to, like, you know those little things you check at the bottom of websites where it's like, I've read all the conditions. This is you reading all the conditions. Now the syllabus is just this monster document that this whole first part, college priorities, I actually have no control over that. That was put in there. I can't move it. I can't do anything with it. So it has to be there. And then it has my contact information. I'm not going to go through the whole syllabus. That's the whole point. I don't want to read through this. But I do want to point out that the syllabus has my cell phone number on it, and you are free to text me, call me if you need help, 24 hours a day, 7 days a week. You know, I do sleep, and I do have a family, so I may not answer, but don't worry about bothering me. And that's because I also teach online, and so for my online classes, I have to be available to them, so I may as well be available to everybody. And I have the phone that I can write on the screen. So what's cool about this, I don't care if you don't like Samsung. Look, this is great for me because what you do is you sit there and you're working on a problem, right? And you're stuck and you're like having trouble, and you will take a picture of the problem. You will take a picture of your work, and you will text that to me. And in that, you can include your name and what class you're in. And then I can sit there and look at your work, and I can try and find a problem. I can circle it, I can add things, I can edit, and I can send you a picture back. And it's just very easy to communicate that way in this class, or with all my math classes. But I just want you to know that you have that option, okay?
And
Now,
it pops up okay on iOS? On iPhones?
will it what?
The thing you just talked about where you...
Well, I'm just going to send you a picture.
Oh,
Yeah, I'm just going to send you a picture. Yeah. But with Apple, you know, they do control you. So I'm not quite sure they will allow that to happen. If they allow you to get my picture, I'm just kidding. Okay, I have office hours. Look, I don't want to read through this. I really don't. But the office hours, this is important because I am available right after class. Okay, so right after this class, I don't have another class till 12:30. And before this class, I can't be here. But and then later on today, from 2 to 3, I'll be available, except today. Today I can't be in my office, so sorry. But then on Tuesday, Thursday, I also have office hours. And then Fridays, if you want to make an appointment with me, I'm on campus, but I can't commit to any time slot because we have meetings that come up different times, all right? So hopefully that works into your life. If not, you have my cell phone number, right? Now, that's it with the syllabus. You read through the rest. It goes through all the grades, how everything's broken down. If you have any questions about that, just get with me. The way this class is going to work is that, you know, I'm going to come up here and lecture. I'm recording this. This video will be placed on YouTube right after class. I'll go to class. It'll take about 30 minutes for it to get published out by YouTube. But, you know, probably by noon today, the video of this class will be available to you. So that doesn't mean you don't come to class. It just means that when you're here in class, you can pay a little more attention to what I'm saying instead of trying to copy everything down and just say, I'll figure it out later, right? So does that make sense? And then also, if you miss a class, you miss a class, okay? It happens, but then you have a video you can go back to, and it doesn't feel like you're walking into something that, like, what happened while I was gone, right? Okay, so we've got that. And then you go home and you do your homework. So I have a schedule here that has the homework assignments, and I updated this. Can I not get this from here? Oh, I have to charge my battery. Oh, I think it downloaded. So I suggest that you print this off. All right. And I know you can't read that, sorry. So it shows what we're supposed to do every day, and then when the exams are, and it also has the homework assignments. So these homework assignments are what you're supposed to do. I don't collect homework. I don't check homework. I don't, this is Calculus 2. I promise you, almost with 100% certainty, that if you don't do your homework, you will not pass this class. If you do your homework, you've just increased your odds of doing better, okay? So this is the bare minimum of what you need to do in order to succeed in this class. Now, let's say you go tonight and you're having trouble with page 181, number 16, all right? Don't go texting me, not yet, okay? Because I also have my homework solution videos. So I've also worked out every single problem on video. So this is a resource for you, right? Now, unfortunately for tonight's homework, I had to do it at my house, and I didn't feel like setting up the camera in the office, so it's it's a screen capture. It's just me writing on a tablet. The rest are just me standing in front of a whiteboard doing the homework. And if you look at these, you'll start to notice how long the homework assignments are, right? And this is me doing them. I know what I'm doing. You know, like I know where these problems are supposed to go. I'm not like trying to figure out, what am I supposed to do with this one, right? So I would easily double or triple each of those times. That's what you should expect. And I looked at it, it's about 3 hours. I would expect about 3 hours per homework assignment, you know, honest time for you. Now, the homework solutions, I've seen people use these the wrong way also. I do not recommend that you watch the homework assignments and sit there and just be like, yeah, I got that. Yeah, I could do that. I get this. I got that. Because, yeah, you can, you know, it's like anything else. You watch someone do something. Yeah, I can watch someone run a marathon and be like, yeah, I could do that. You know, I might get tired, but I could do it. It's just like that. You actually have to go out and run a mile before you think you can do 26 miles, right? So here, what you should do is you should start working the problem out. Have the video available, and then maybe work the first part of the problem, and then maybe turn on my video and play it and see if we're on the same page. And then continue working it yourself, and then just use it as a check. All right? So that's the way I recommend you do the homework. Now, if after this you still are having issues, right, then contact me by text and phone. And I'm not trying to discourage you from contacting me. It's not that I don't want to hear from you. It's that if I have to go refer you back to one of these videos, that's going to kind of irritate me a little bit. Because I spent a lot of time putting this out here for you. And to have me just go find it for you in this video and like timestamp it and send you the link is kind of irritating. It shows me that you're not really putting in the time. Does that make sense? Okay. All right. Any questions on that? All right. Then other than that, I think I'm ready to start.
Can you show us the lecture notes?
Oh yeah, the lecture notes, thank you. During class, I will be following a set of pre-made lecture notes up until we get to certain sections. Okay, when we get to the areas and the volumes, I just for some reason have never wanted to put lecture notes out for that because everything is so visual and sequential. I like to just put it on the board. So there are lecture notes for the first few sections or first few chapters, and you're free to print these out. The problem is they are not going to have any of my interactive diagrams because all these things are things I can interact with here, and so but they're like PDFs of this. All right. So all of those are located in the course files. They should be unless I pulled them. Course notes, and then here they are. Okay.
Thank you.
Yep. And there might be some typos in these. I've never gone back and fixed them because, again, they're just there to help. Yes?
Question, is there going to be any chances for extra credit like last semester, like if we form a study group or come during your office hours?
I think there's enough questions in this class that I'll be able to give you some challenge questions as bonus.
Okay.
Yeah, but nothing for like forming groups and studying together. Yeah.
You have formula sheets? Is that going to be something?
Yes, you are allowed to have formulas on the tests, okay? So I know this is a huge like philosophical debate in our department, but you know, I'm of the opinion that in the real world, you're probably not going to be doing antiderivatives to begin with, but you know, in the real world, you're never really put into a closed room with no resources and asked to solve a problem, right? Even if you're an engineer, like you're going to use every resource you have. So I believe in formula sheets because if you use them, then you should know where to go to find what you need, right? And that means you've been using it, and that shows a certain level of thinking, all right? So yes, these are the formulas. You can print every single one of these out and bring them to every test. Now, you won't need them all right away. You'll just probably, for the first test, you'll just probably need the first one and maybe this one. But print them all out, bring them all to the test. Now, you can't edit them. You can't add your own little cute formulas. You can't use your unit circle from pre-cal that you've had underneath your pillow for the last 3 years. Like, everybody in the class has to have the same resources. No unfair advantages to anyone. So this is it. This is all you get. So I would recommend that you go print this out take a look at it, see what's there, what's not there. The things that are not there, like it does not have a big drawn unit circle. All right, it doesn't have it. So, you have to be comfortable with the unit circle. We good? Yeah, I think that's it. Let's do it. So I was talking to my wife last night, and I said, do you think it's a bad idea that I'm going to give them a quiz on the first day? And she's like, So she didn't fight for you guys. So that's what we're going to do. So clear your desks. I know, it's terrible, isn't it? Hopefully you brought a pencil or a pen. I prefer you write in pencil. Did y'all hear me? I prefer you write in pencil. In fact, I mean, when I look at, when I grade somebody's paper that's in pen, what that's telling me is that person does not believe that they can make mistakes. All right? All right? I consider myself a pretty good mathematician, and I've always written in pencil. I've never, ever written in pen. So at least for this class, I encourage you to write in pencil. Because if you take a test and you do it in pen and you start scratching things out, I'm going to look at that in a negative way. All right? Okay, so let's do this test quiz. Keep it face down because it's timed, and I don't want anyone to have more time than anyone else. So just wait for a second. Don't panic. It is 1 plus 1 squared cubed, and then take the 8th root. Oh, quizzes will come in any form. Yeah, you'll have group quizzes, you'll have take-home quizzes, you'll have, hey, you were here today, 100. All right, don't turn them over yet. Make sure everyone has one. Before we take the quiz, I just want to mention that, I said something about, in the real world, you won't be ever probably doing antiderivatives unless you're, I don't know, doing research or in the educational field teaching someone how to do antiderivatives. But the whole point is that, like I said, this history, is leading up to something. If you're doing engineering, in the real world, they have to use like Fourier transforms. Like if you don't know what a series is, the Fourier transform is going to make no sense to you at all. So there is some aspect of this that is important. All right, now we're still like fundamentally building up the foundation of the pyramid towards what your field's going to be. But the bigger picture, this is about, I've talked to many people in the real world, right, who are engineers, who are computer scientists. And when we're sitting there in some social, function, I'm asking them, like, what is the big thing that my students need to know in calculus, to get into the real world? Like, what's the big thing? And it always comes down to one thing. It always comes down to critical thinking. Critical thinking, problem solving. Okay, are you the type of person who faces a challenge and kind of curls up in the fetal position, like, oh, poor me, this sucks? Or are you the person who has to like keep throwing yourself into this until you break through? And then you get that pleasure, that deep pleasure when you actually understand it and you get through it. Are you the problem solver or are you not? Are you a critical thinker or are you not? If you're not a critical thinker or a problem solver and you're in a STEM field, you're probably in the wrong field. All right, you know what I'm saying? So with that said, I just didn't want to leave that out. This is a timed quiz. This is a kind of a let's see where you are type thing. I just want to see where everyone is. I want you to do your own work. And there's one catch to it. It's 10 problems. You can't do number 3 until you've done 1 and 2. So everything has to be done in sequential. Like, so if you get number 9 right, I'm not going to count it right if you skipped anything between. So you have to go sequentially through this. That's the deal. Go. 10 minutes. Oh, you can answer them there or on separate paper. Sorry, I forgot I didn't really give you a bunch of room to write. You can probably squeeze it all in though.
I think I did.
You have a bunch of pens?
Oh, yeah.
$1 a piece? Okay, are you willing to loan those out?
Oh, yeah.
Okay, so anyone need a pen? We're good? Just one? Just make sure you get the pens back to whoever you borrowed them from, okay? We're good? Okay, so look, the point of this quiz was not to scare you, intimidate you, or anything like that. I just really honestly need to know like where everyone is with this, all right? Maybe it's been 2 years since you took calculus. Maybe your summer was like non-stop partying and you don't remember anything now. Whatever, it's no big deal. I just want to see where you are, all right? So you're going to grade your own paper now, all right? And you're going to do it in pen. So just for the sake of making this easy, I want you to assess yourself, giving yourself the possibility of 10 points per problem. So let's do it this way. Like, if let's say, like on number 1, if you miss number 1, take off 10 points, okay? If you miss number 1. These are the answers. But like, let's say on number 2, you forgot the 6. I want you to decide for yourself how many points you think should be taken off there. All right? Yes?
Does it need to be, like, for number 2, for example, does the order matter?
No, the order is multiplication, doesn't matter. So you can have your 6x back here, it's fine. Yeah, I don't need it cleaned up. But you should have a 6x times a cosine 3x squared. All right, yeah, so I want you to grade yourself, take off however many points for each one. But I want to talk through these, okay, real quick. So, I mean, yes, the derivative of sine x is cosine x, right? Okay. All right, derivative here, we have to use which rule? Chain rule, right? So you start by taking derivative of the outside function, which is cosine. So you have cosine of the inner function. And then times, chain rule says multiply by the derivative of what's in here, which is 6x. And I just threw it out in front, okay? Now, on number 3, you have what going on here? Product rule. You have 3x squared times sine x. So you have to use a product rule, which would mean you take the derivative of this one times this one plus the derivative of this one times that one. And again, this order doesn't matter and this order doesn't matter. And in fact, you could switch, where'd it go? You could switch like that also. All right?
Yeah, I factored.
Yeah, you can factor also, but okay? Now for number 4, you have what going on? A couple of chains, right? You have composition, you have sine of 3x squared. So you have to first take derivative of the outer sine function, which would be cosine of this entire argument. Then times, now you've done that sine, so you have to go inside, take derivative of that sine. So you have cosine of the argument of that function, which is just the 3x squared. And then you go inside there. You've done that already, so you go in there and take derivative of that, you get 6x.
Oh,
Yes?
on number 5, is it okay, because you have 2?
I have 2 times 6? Oh.
Yeah.
Yeah,
12x.
12, yes. That's just arithmetic. I left it like this because I wanted to be able to talk through it and see where everything came from, right? So with this one, this is also chain rule. So with chain rule, we have to figure out what the outer function is. And the outer function here is the squared function. That's the last thing happening. So we have to take care of, you have something squared. So the derivative of that, the 2 comes out, and then you have this right here. And then you have to take derivative of the sine of this, which is cosine of it. And then you have to go inside the sine and take derivative of that, and that's here. And then, yes, you could move this 6x out here, and it would become 12x. All right? But I also left it this way intentionally because does anybody know what we could turn this into?
Oh, is that that's a double angle?
That is a double angle. Sine of 2u is equal to 2 sine u cosine u, isn't it?
Yeah, so that would be sine of
So this would be
2 times
sine of 2 times 3x squared, so 6x squared. You could have rewritten this that way. I didn't anticipate anyone would do that. Did anyone do that? No. But I left it like that because I also wanted to point out you could do that, right? And then it would just...
It wouldn't be wrong if it wasn't like that.
Oh yeah, it's not wrong. It's not wrong. It's just, if you look in the back of a book, not better. You look in the back of the book and you're like, what the heck? You know, like they have that answer, you're like, what the heck happened? Well, that's what happened, right? It's just things I'm pointing out, that's all. Okay, so number 6. Number 6 was another chain rule, but I wanted to make sure that you were comfortable with derivatives of e. So derivative of the exponential function. The derivative of e raised to anything is itself, right? And then you have to do times the derivative of the exponent. And so you have to take derivative of sine of 3x, which is cosine of 3x, and then there is a 3 outside of that. Times 3, because you have to take derivative of the 3x in here. All right, number 7 is another composition, but this time you have to start with the sine. The derivative of sine of something is cosine of it. Then the derivative of what's here is itself. And then times the derivative of what's up here, which is this. Remember, I was trying to tell you the story. If you can't walk forward, it's going to be very hard to walk backwards, right? We're just looking to see how comfortable you are walking forward here. All right, now, derivative of, this is a natural log. I hope you could see that that was natural log. Derivative of natural log of something, right? The derivative of natural log of something is just 1 over that something. And then times the derivative of what's here. And this is a product rule, x times sine x. So you have to do like a little mini product rule on this right here. And that's what I did right there. That's my product rule. You'll see my product rule? And do you have to have that little product rule in parentheses? Sure. Absolutely. This either has to be in parentheses out here, or you can slide the whole thing up on the numerator, and that's fine also. Questions on those? Yes?
You said it has to be in parentheses, because I just put like times and then...
Like without this?
Yeah.
That would be incorrect, because what you would be saying is it's just this times this plus this, right? As opposed to distributing this to both terms, which is the correct. Correct. All right. So I don't know, take off point or two, whatever you think, right? Whatever you think, that's where I'm having you grade your own just so you can see how we're going to have very different opinions on how much to take off for something, right? So don't inflate your grade, but then don't kill yourself. Don't be like, oh, I missed the parentheses, minus 10. You know, like it's not that bad. Okay, this one. So now I switched over to a different notation. Instead of using y prime, I use this notation. Does anyone know what this notation is called? Usually we call this like the prime notation, but this is called Leibniz notation. Leibniz. Oh, yeah. There's 2 fathers of calculus, Newton and Leibniz. They both developed calculus at the same period of time in history, 2 different places in the world. They were doing the same thing. It was kind of interesting. But this is the notation that Leibniz used. This is the notation that Newton used. And there's advantages and disadvantages to each. All right, so for this one, I give you an equation. I ask you for dr dt, which is the derivative of capital R with respect to little t, and little t does not appear here. So this would be like a related rate problem. So you have to take the derivative on the left side, and pi is a constant, so it just stays here. Then derivative of r squared with respect to time, you have to first apply the power rule, which the 2 drops out, so you get 2r. But then you have to take the derivative of r. And the derivative of r with respect to t would be dr dt. And then on the other side of the equation, you just take derivative of a, and you get dA dt. Okay, good? And then number 10, this is an implicit differentiation problem. It's kind of like number 9, except you're differentiating with respect to, oh, shoot, I said t there, oops. Well, this answer is wrong then, because I meant to say dy dx. But I would put dy dt. That means you have to treat all these variables as if they depend on t, so the derivative of x is not going to be 1. The derivative of x should be what? Did anyone get to this one? Yeah? So, yeah, let me just, yeah, that should be dx dt. Okay, so let me put the correct one up here. This was supposed to be x. All right. So what you do is you have to take derivative of this with respect to t, and that's a product rule.